name is Chen, and I'm from National Yat-sen University, Taiwan. The topic I'm going to present is an effective neural architecture search for bike sharing system demand prediction. This page shows the outline of this presentation. We will first talk about the factors that inspired me to do this research. Next, I'm going to introduce the proposed method. The results and conclusion will be presented in the following section. And the final part is the future work that I hope can improve the whole research and apply it in the real world. The first reason why I do this research is because the spatial temporal network prediction is recently being a hot topic in the world. More and more deep learning methods are proposed on the network prediction, such as internet traffic and transportation flow. Among these problems, the station demand prediction of bike sharing system, as known as BSS, is a critical issue in Taiwan because of the dramatically growing number of the dock-based stations. In order to solve these real-world problems, the deep learning methods are often used for its great performance. However, the manual design of model architecture requires background knowledge of the problem and lots of experiment support, makes it a time-consuming procedure. So I propose a neural architecture search framework and use adaptive simulated annealing genetic algorithm as this searching strategy, which will be referred to as ASAGA in the following slide, to automatically create a well-performance model on the BSS station demand prediction problem. Now, I would like to introduce the first idea of the method, which called the neural architecture search. Since the traffic flow is affected greatly by the spatial and temporal factor, so the deep learning model will be mainly constructed by CNN and LSTM layer, and the corresponding features can be captured by these layers properly. The input features of model are the volume and flow value of each bike station. For each layers in the model, different architectures will be set as several choice blocks, and be sampled equally in the face of training supernet and searching-based model. Different CNN kernel size, putting layers and activation functions in blocks will provide a huge number of architectures, which means more possibilities to find a better model. I will present the details of choice block later in the next slide. SuperNet is the model network that contains all choice blocks that mentioned earlier, which will be used to train the weights of different architectures before searching the best model. This figure is the overview of the choice block and cell component. As we can see in the left upper side, model will take volume and flow feature as input, and 3 cell component is designed to contain the choice blocks. For each choice block, different architecture will be uniformly sampled, so their weights can be trained equally. The proposed framework is operated as 4 phases. First, the SuperNet training phase makes all the architectures train uniformly, so there is no need to train all models respectively, which costs lots of time and computational resources. In the following phase, a meta-heuristic algorithm called ASAGA, which combines SA and GA to find the best architecture in the SuperNet. After finding the architecture, third phase retrain it and finally evaluated by the test dataset. The ASAGA is based on traditional GA, which contains crossover and mutation operators. Furthermore, SA is adopted in the selection operation to provide the probability of accepting offspring, which means the model architecture with worse performance. This modification can improve the ability of traditional GA to find the best solution, which also means it costs more time since the slower convergence. However, it is still negligible comparing to the procedure of training deep learning model. For each candidate solution in the population, a set of architecture of different choice block is included, which can be altered or changed in the crossover and mutation procedure. The crossover operator randomly chooses a point from two parent solutions and switch fragments to generate a new offspring solution. Then the single architecture might be mutated according to the small mutation rate. The fitness function will next evaluate the offspring with RMSE result, then determine whether to replace the parent with lower accuracy or discard it. But the SA algorithm here provides the probability to accept the offspring with worse result, prevent the local optimal solution. Based on the method mentioned above, the reason why the proposed NAS framework is more efficient is because the fitness function can share the weight from SuperNet instead of training the candidate architecture again. Meanwhile, the searching strategy also guarantees the performance of the architecture searched by ASAGA. The result shows that the proposed framework ASAGA outperforms the other methods such as ARIMA, LSTM, and the state-of-the-art HCDM model in both MAPE and RMSE criteria. And the start and end category in the figure means the prediction target is focused on whether the start or end of the predefined time slot. As we can see in the previous slide, even the prediction result of proposed method outperforms the original model. It still seems like a limited improvement from the experiment. To achieve satisfactory progress, the variety of searching space and SuperNet must be increased. In addition, there are some specific stations have the worst accuracy after observation, so find out the reasons that cause this result is also helpful to the improvement. Finally, to apply the framework in a real-world BSS, decreasing the training cost of SuperNet will be the main challenge, so the prediction problem can be used immediately by the system maintainer. Finally, I would like to thank for the huge experiment support and progress improvements by my university classmates Chao-Yen Huang and Yun-Ye Tsai, and advising by my supervisor Chun-Wei Tsai. And this page shows the reference of my research. Thanks for all your listening, and please contact me by email if there are any questions or further discussions. Thank you.